Morning guys. Yesterday we were discussing about the electric field produced by electrical dipole. Today we are going to discuss about what happens if we put an electric dipole in a uniform external electric field. Now uniform electric field means that in that region at every point the magnitude as well as the direction of electric field remains same. Now we denote it as parallel equispaced lines. So suppose this is uniform electric field. Now if we put an electrical dipole here, here it is minus q, it is plus q. So it will align itself along the field direction such that the dipole moment vector and the electric vector remains in the same direction. Now since the electric field is uniform, the force on this charge is QE acting along this direction, and the same on this one is magnitude is QA and acting in this direction. So here the total force acting on the dipole is 0. Now the total force is not only 0 but also the point of application is same. The point say this one, so this force is acting along this line and this force is acting along this direction and along this line. So there is no force as well as there is no torque. Now suppose we rotate it little bit by an angle theta. So now the force on plus q is along in this direction, QE, and force on this one is along in this direction, minus q. Now here again you can see this force is in this direction, this force is in this direction, which are completely opposite to each other, and the magnitudes are also same. So again in this case the total force or net force will be 0, but the point of application of the forces are different now. So there will be a torque. This torque will align the dipole again in like this. So we have to find the magnitude as well as the direction of this torque. Okay, now the forces are equal, so we can write the torque as magnitude of the force, either one, multiplied by the perpendicular distance, which is this one. So if the length of the dipole is 2a, this is theta, that means this is also theta. So this perpendicular distance is 2a sin theta. So the magnitude of torque, which we denote as tau, will be equals to magnitude of the force, which is QE, multiplied by perpendicular distance between the forces, which is 2a sin theta. Now we already know the dipole moment of this dipole. The magnitude is 2qa. So 2a and q, we can write it as p. P is dipole moment of the dipole. So p is sin theta. So this is the magnitude of the torque if we rotate it by an angle theta. Now we have to find the direction as well. Now we already know that p is also vector quantity, e is also vector quantity, and so is torque. So we have to find a vector relation between them. Now you can easily see the direction of electric field is along this. Here the direction of dipole moment is along this. This is theta. So if we rotate from P to E, that will be the direction of the torque. Okay, so you can write tau equals to, this is P sin theta, in vector you can write P cross E. P cross E has the direction perpendicular to this plane and outward direction, and because of the rotation the torque will also have the direction like this, outward perpendicular. So this is the torque, the derivation, this derivation of torque or the formula of the torque. Now what if the electric field is not uniform? Okay, let us consider simplest case. Electric dipole is here, minus q plus q, and say the electric field actually increases in this direction. The direction of the electric field is in this direction. Also, it gradually increases in this direction. So here the field intensity is more than this point. So at this point the net force is along this direction. At this point net force is along in this direction. Since the electric field at this point is more, so net force along this direction will be greater than 0. Okay, so it will actually start moving in this direction. The dipole as a whole start moving in this direction. Here if the electric field is uniform, it will remain stationary. Okay, now if we, in this case we have put the dipole parallel with the electric field, and if we put it anti-parallel, plus q here and minus q here, and say the electric field gradually increases in this direction, in that case the force on this will be along this direction, force on this will be along this direction. So in that case here the force will be more, so the net force will act along this direction. So in that case the dipole will move in this direction where the electric field is less. So this is all about dipole in an external electric field. Now, so far whatever system we have assumed, the systems were consisting of point charges. Okay, we have found electric field due to various point charges system, like a triangular system. Now how will you calculate the electric field if the system is continuous? For example, suppose we have a linear, any kind of wire or anything which has some charge. Suppose its length is L and total charge it has is Q, and we have to find the electric field at this point, say P. How do we calculate it? For that, first of all we consider a very small point so that we can treat it as a point charge. Okay, suppose its length is dl. Now if the charge is uniformly distributed, the charge per unit length, which is called linear charge density, denoted as lambda, which is q by L. The charge per unit length will be q by L. So charge of the small element will be dq equals to lambda dl, which will be equals to q by L dl. So you can easily find out the electric field if the distance is r. You can easily find out the electric field at this point P due to the small element, say it is dE, 1 by 4 pi epsilon naught dq divided by r square. Now to find the total electric field, we have to take the contribution of the whole line. So in that case we have to do integration. So depending on the system, you can easily put some limits and you can find out the electric field at this point. So this will be like dE dq by r square. Similarly, it is also possible, instead of a line there can be a sheet, a plain sheet like this. Okay, and it has total charge say q, its total surface area say s, and we have to find electric field at P. Again in similar fashion, where we are assumed a small line element, we can similarly consider a small area element. So if its total charge is q and total surface area is s, so its charge per unit area, which is q by s sigma equals to equal surface charge density. Now in similar fashion we can easily find out electric field equals to, again we first find the electric field because of this point. Its charge is dq will be equals to sigma into, say this area element is ds, sigma ds, and again putting in similar way we can find out by epsilon naught dq by r square, and you just put the value of dq, and depending on the situation or system you can easily calculate this. Similarly we can do it in the for any system of volume, not surface but a volume, so sphere or anything else. Okay, but the application of this type of systems are out of our context, so we'll just keep it. Now if any system has some symmetry, we can find the electric field due to this type of system using Gauss's law easily. Now we need to first study the statement. Now it states that the total electric field passing through any closed surface is 1 by epsilon times the charge enclosed by the surface. So suppose we have any closed surface, okay, this is not a 2D, this is a 3-dimensional figure. Okay, say it has contained q charge here inside it, so the total flux that will pass through it will be phi equals to q by epsilon naught. Okay, we only have to see the charge inside it, that net charge inside it. Okay, if there are any charge outside, we do not have to calculate them, because if the charge is outside, say here a charge, point charge, the flux, the field lines that are entering, the number of field lines that are entering and the number of field lines that are coming out of the surface will be same. And the entering field lines will give you a negative flux, and the field lines that are coming out will give you a positive flux. So that amount will be same and they will cancel out each other. So we will only have to calculate or take into account the charge that is enclosed by the closed surface. So this is the statement of Gauss's law. Now we can apply it to various systems and we will find them in the next lesson.